Hello everyone. I hope everybody will be having great time at the conference. Today I'll be presenting our work on scaling the Laplacian score algorithm for feature selection using distributed computing. Lately, the data that is being generated is high dimensional and with millions of instances. We face challenges when using this data in application due to the presence of numerous redundant and irrelevant features, which leads to increased computation time as well as it also degrades performance. Feature selection has thus become an essential task in machine learning, data mining, and pattern recognition. But traditional methods often struggle with current scale. Moreover, as datasets are becoming larger, many organizations prefer to maintain distributed databases for scaling their data horizontally, and traditional algorithms are not compatible with these type of databases. Our work addresses these challenges head on. Myself, Madhav Kadam, I'm senior undergraduate student in computer science, currently doing research for my final year project under Professor Aruna Tiwari's Computational Intelligence and Big Data Analytics Handling Lab. I'll be presenting our work today. So I'll first introduce everyone to the Laplacian score algorithm and then walk you through our proposed modifications in the algorithm, after which I'll share some significant results that we were able to achieve, and it will end with the conclusion and future scope for our work. So let me start with some context. As I said, feature selection has become fundamental as it helps us identify the most relevant features. This not only improves computational efficiency but also enhances the model's performance and interpretability, making models more comprehensible, which is very important. While numerous feature selection methods already exist, many are designed for supervised learning scenarios where we have labeled data. The Laplacian score, which was introduced by Hay et al. In 2005, stands out as a powerful unsupervised feature selection method. It's particularly valuable because it can work effectively without class labels, making it suitable for both unsupervised and supervised learning contexts. The key insight behind the Laplacian score is its focus on preserving the local geometric structure of data, which is crucial for discrimination tasks. So as you can see, we have provided the original Laplacian score algorithm calculations. So first of all, we need to note that the Laplacian score is calculated for each feature. For this calculation, we need a nearest neighbor graph where nodes I and j are connected or are said to be close if each one of them is among the k nearest neighbors of others. In supervised learning scenarios, we say they are close if they share the same label. To populate the weight matrix, we can use any kind of function which diminishes as distance between two data point increases. Original paper uses, as you can see, Gaussian kernel, but other distance functions can also be used. Weight matrix helps us capture the local structure of data space. To calculate the matrix L, we need to subtract weight matrix from a diagonal matrix D, where each diagonal entry of D is calculated from corresponding row sum. So with the formulas that are specified for LR, we can calculate the original Laplacian score, but it possesses some significant challenges, which we can see in the next slide. So we identified three major challenges with the original Laplacian score algorithm. You can see the explicit calculation of the weight matrix S for the nearest neighbor graph is required with whatever the distance function we will use. Then there multiple matrix vector multiplications are also required, which results in a O of n square complexity, and O of n square auxiliary space is also required for matrix storage. To address these challenges, we introduced several innovative modifications. The core of our approach lies in transforming the matrix-based computations into a sliding window representation. This transformation will allow us to compute the Laplacian score based on individual data points and their respective nearest neighbors rather than working with entire matrices. So, let me explain our reformulation in detail. The key insight, as I said, is we use unidimensional data, which is how most real world features are represented. We can leverage the inherent structure of the nearest neighbor graph, where there will be only at max order of kn edges. So for larger data sets, in order to focus on individual data points and their k nearest neighbors, and to avoid full of n square operation and storage, we calculate this numerator term. We calculate this numerator term and denominator term separately, which we can see here. So this is the reformulation for denominator term, you can see the matrix calculations are reformulated into individual data point calculations. Same goes for numerator calculations, and combining the terms computed earlier, we get our this new formulation which can now be used to compute using sliding window across sorted data points. So after sorting each feature, we ensure that the positional indices of the nearest neighbors are within the bounded range of minus k to plus k relative to the current index, where k represents a predetermined number of nearest neighbors. This leads to an elegant sliding window approach where the window size ranges from k to 2k, traversing the ordered data and capturing the local neighborhood structure. However, implementing this wasn't straightforward. We encountered a challenge where determining the start and end indices becomes complex because the nearest neighbors of an element are influenced by both past and future of that element. So, to solve this, we introduce what we call the history queue. This queue maintains records of the last k processed elements, allowing past elements to access their future elements. The history queue enables lazy evaluation when its length is about to exceed k. We calculate the sliding window contributions of the oldest element. This approach reduces the time complexity to of nk and the auxiliary space complexity to of k. But our work doesn't stop there. To make this algorithm truly scalable, we implemented it using Apache Spark, which is a powerful distributed computing framework. This implementation required careful consideration of data distribution across multiple nodes and handling boundary cases effectively. To make our algorithm readily available for use across organizations, we chose Apache Spark because most organizations might prefer to have their distributed systems in Spark, and it also provides compatibility with models and frameworks that can perform various operations on the processed data. Apache Spark also provides resilient distributed data sets, that is RDDs. So in our distributed implementation, we made few practical assumptions. First was that the dataset is distributed across multiple nodes in a decentralized fashion, where each node is responsible for a subset of data. Second is that the each node processes a substantial amount of data such that the partition size is significantly larger than k. One of the most challenging aspects was handling the boundary elements between partitions. First and last k elements require data from adjacent node, posing cross-boundary computation issues. The first k elements in a node will require access to previous elements that may reside in a different partition, and the last k elements will need iteration and lazy updates from data in the next node. So this leads to a cascading effect, and to address this, we divided our calculations further into two phases. So instead of computing an element's contribution only after its end of window has been lazily maximized, we split the summation into two parts, from start to current index and from current index to the end. So this innovation enabled more preemptive calculations and eliminated the need to store window start position in the history queue. So let me show the flow diagram so that we can hopefully discuss it better from a high level view. For low level details, I will strongly recommend everyone to read our paper where we have discussed and provided each algorithm in detail. The implementation consists of two major components, the worker node algorithm and the driver node algorithm. So each worker node possesses a partition of data, and it processes this partition locally with a linear pass using history queue and gets its partial contributions done. So then these partial contributions are basically a bulk of computations within each partition, and after getting partial contributions from each worker node, driver node manages the cross boundary calculations and aggregates the results, and at the end we get the Laplacian score for each feature. So we have validated our approach through extensive experimentation using 6 datasets, which includes 5 real-life soybean genomics datasets and one UCI machine learning repository dataset, which is a pen-digit dataset. So the results were compelling. We ran our algorithm over 1, 2, 4, and 8 cores. For smaller datasets like rice chromosome 1, rice chromosome 2, and pen digits, where we were able to compare our results with original Laplacian score method, our approach showed significant speed improvements, which I'll share in next slides. And more importantly, for larger datasets like AMSOI, WO5, and FISCAB3, where the original method failed due to memory constraints, our approach was able to successfully compute the Laplacian score. I'll share the results. So the scalability of our solution is particularly evident in the timing results. When we double the number of cores from 1 to 2, 2 to 4, and 4 to 8, we observe nearly linear speed up. For instance, with the AMSOR datasets, as you can see, the computation time decreased from 46.14 seconds with one core to 8.60 seconds with 8 cores. What makes this result particularly significant is that they demonstrate not just improved efficiency but enabled previously impossible computations. The original Laplacian score method failed with out of memory errors on our larger datasets while approach handled them efficiently. Our algorithm becomes more and more useful with increasing data size as the original algorithm was quadratic in time and memory complexity. So from a theoretical perspective, our method achieves a time complexity of O of kn by p in a distributed setup where n is the number of instances, k is the number of nearest neighbors, and p is the number of partitions. So since k is typically small relative to n and can be treated as a constant, this represents a substantial improvement over the original O of n square complexity. To conclude, our work makes three primary contributions: a novel sliding window reformulation of the original Laplacian score computation, an efficient distributed implementation using Apache Spark, and empirical validation on real-world datasets demonstrating both scalability and practical applicability. The implication of this work go beyond only the scalability because we make our algorithm readily available for implementation to organizations using Apache Spark with effective boundary case handling. This is particularly relevant in domains like genomics, where high dimensional datasets are common and unsupervised learning is often necessary. So looking ahead, there are several exciting directions for future work. We could explore adaptive techniques for determining optimal partition sizes and nearest neighbor parameters in distributed setting. We can also explore other spectral based feature selection methods. Finally, I would say our contribution make the Laplacian score a viable feature selection method for modern big data applications. Thank you for your attention and patient listening. I am open for any questions.